In previous modules, we learned how functions can be used to create self-contained modules of code. Consider a case where we're writing a program to process students' information. This information could include data such as an ID, age, and grades. For the sake of simplicity, let's imagine we only have 2 courses to worry about. Additionally, we won't take into account textual information such as the student's name either in this example. We'll learn about handling text in a later tutorial. So our student will have 5 pieces of information: an ID, an age, 2 grades, and a GPA or grade point average. Functions can be written to process this data, such as one to print a report. In this function, we're taking all the student data as parameters and outputting it to the console. Incidentally, you can specify the number of decimal places displayed by a float by writing something like %.2f when you print the number. This outputs a number with only 2 decimal places. Looking at the design of this function, we might notice a few problems. First, for every student, 5 variables must be created and initialized. If we have even 5 or 6 students, that's a lot of variables to keep track of. Next, our function takes in these 5 values as parameters. 5 parameters is actually quite a lot to pass in. And also, any change to what information the students in general have, for instance, say we want to add in a 3rd grade, that would require changing the code for all these values and all the functions that use them. The key thing about the data we're working with here is that it's all related. All this student information needs to be kept together, but with the tools we have right now, that's pretty difficult. Ideally, we want to have just one bundle of data per student. In order to accomplish that, we could use a structure. A structure is literally what I just described. It's a bundle of data defined by the programmer, a user-defined data type. As far as the program is concerned, this structure is a single variable. However, inside this structure are more variables. Think of it as a bag. You don't want to be toting around all your things individually, so you stick them in a bag. If you want to give someone a bunch of stuff all at once, you wouldn't hand them the things one by one, you'd just give them a bag with all the stuff in it. Shopping bag, packed lunchbox, backpack, it's all the same idea. The only catch in this analogy is that structures are all predefined. They contain a specific set of variables. So what we're doing is creating a template for this data bundle, which we can then refer to later. Setting up a structure is pretty simple. First, you need to define the structure. We write struct to indicate that we're creating a structure, followed by the name we want this data type to have. In this case, we'll call it student. After that, we include the variables we want as members of our structure inside some curly braces, and cap it off with a semicolon. Now we just bring our variables into the structure. So at this point, we have just a single data type, student, and a student will each have an ID, an age, 2 grades, and a GPA, just what we want. Bear in mind that we don't initialize these variables here. Like a function prototype, all we're doing here is telling the program that we're going to be talking about a special data type, and this is the format it'll take. Back in main, we can create new instances of student just as we would normal variables. This means that each of them still need to be initialized just like any other variable. And to do this, the individual member variables need to be accessed via the structure itself. This is done by writing structurename.memberName. For example, to access the ID variable, we'd write s1.id, since s1 is the name of our instance of the student structure, and id is the name of the member variable we want to access. Aside from the new way of accessing them, the variables inside a structure work just like normal variables. s1.id is an int variable and can be used just like any other int data. Structures are modules of data. This helps us organize our program better, as well as create and transfer data more efficiently. So now that we have a structure set up, let's go back to that print function. In C++, you can actually have two or more functions with the same name, provided they take different parameters. This is called function overloading and can often be really useful. Let's say for the sake of argument that we want to still have access to our old function, which takes individual variables, and a new one which will take our student structure. These functions will have the same name, but different parameters. Overloading allows us to have these two definitions and keep the same name. Ordinarily, C++ wouldn't allow you to have function names that are not unique. But with the parameters to differentiate between the two functions, the compiler can tell them apart by the context. If I pass in a student to the function, it's pretty clear that I want to use the version that takes a student. A more pertinent example would be that averaging function we looked at a few videos ago. If you recall, that function originally took ints, but we changed it to take floats because you lose information by dividing integers. With overloading, we could simply have had two versions of that function with the same name, but different parameters. That way, you can call it and pass in ints or floats as you desire, and always get back the appropriate value. Anyway, enough about overloading. Let's start using the student structure. Our new version of the print function will take a student as the parameter, which will be called st. To access the student's variables, we just need to preface the variables with st dot to indicate that they belong to the structure. And that's all that needs to be done. Now we can pass in our students to this function as the sole parameter. This is much nicer than using half a dozen individual variables. Similarly, we can create other functions that receive the student structure and perform other processing on it. The first one we'll look at is called calculate student average. This one takes a student and returns their average grade. We'll use this to process an existing student. The second is called getStudentInfo and won't receive a parameter, but will instead create a new student. It first sets the members of the structure to the data entered by the user, and then uses the first function to calculate and assign a GPA. This student then gets returned. This is the function we'll use for initializing a new student. To actually use these functions, we can go to main and create a new student. We then assign the value of the student to what's returned from getStudentInfo. Then we call printStudentInfo. Let's look at a different problem, a library system. We can define a new structure for a book. Each book will have an ID for itself, an ID for the person borrowing it, and the due date. The IDs can both be ints, and the due date can be a data type from the C library called time_t. There's something we should mention before we continue. Our system will assume that IDs are positive. A value of -1 for the borrower will mean that the book is available to be borrowed. Once someone takes the book out, this value will change to become the borrower's ID. The reason for this assumption is that before you initialize a new variable, its value will be whatever was in that part of system memory. This value is garbage and will be of no use, which is why we immediately replace it by initializing it. It's common for a variable to be initialized to a specific known value that is not valid in the system. In our case, we're using -1. Using null or 0 is also common. Like our student example, we'll have a function to initialize our book called getBookInfo. This will generate a new book, ask the user for the book's ID, and set the borrower ID to -1. This new book then gets returned. To borrow the book, we have another function, borrowBook. This one takes a book as a parameter, checks to see if it's available, and if it is, asks for the borrower ID. Finally, it sets the due date to be 7 days into the future and returns the book structure. We also want a function to give the book back, called returnBook. All this one does is set the borrower ID to -1, then returns the book. And for our last function, we need to print the book info. We'll want to show the due date by converting the time, which is in seconds, to a day, month, year format. There's actually a pre-existing structure for this called TM, which holds detailed values such as seconds, minutes, hours, days, and so on. We can use a function called localTime, or its safe version, localTime_s, to read a time_t value and fill the TM structure. We can do this here and display a user-friendly version of the time. We can access this TM structure just like all the other structures we've worked with thus far, using the dot notation.